Thank you, Maureen. So it's a pleasure really to listen to you and to share this hour with you. So to everybody, good afternoon. I don't know if you are still in the afternoon or you are in the morning or in the evening. It's very impressive to listen to see that you have people all around the world who can listen to you. Okay. Donc, now, I had a picture before. Non, je peux pas. Okay, comment je change mes... Non, je peux pas changer. Non, ok. Comment... Attends, je voulais aller dans l'autre sens. Voilà. So, this is my introduction. Welcome to the Solid State Physics Lab in Orsay. I am walking to it. Then I am still here in a room on the top of this building. And also, I am waiting for you in the microscope room where I have spent many, many years over the past decades with my favorite microscope, the vacuum generators HB5 STEM. Okay, so I have chosen tonight for my discussion, my presentation, to speak of nanoworld. Nanoworld, which we want to see, to measure, to analyze. And for that, we have developed here in Orsay a multi-signal scanning transmission electron microscope. So why the nanoworld? Because the nanoworld raises many interrogations. It can generate risk, and because of that, it is the whole population is a bit afraid if there is some uncontrolled use of nanoparticles. And that is mostly because you can't see it. You can't see it. We can't see it. So it is responsible for its alarming power. So one solution, and we are microscopists, so it's obvious for us, is to transform the unknown world into a known one. So we have to use new tools and develop to see, to measure, and to analyze the world at the nanometer scale. Just a few images to introduce my talk and what I understand as nanomaterials. So this is a selection of objects that we have looked at and studied with our machine over the years. So you see, for instance, interfaces between two materials. You see nanowires, nanorods of metals, and so on. And also in biological material, you can have some diamonds, so nanodiamonds to emit photons, and you can have it directly in cells. So it's a very large field of research. So this is a basic slide to begin my talk. Why do we require an electron microscope? In the electron microscopes, you have an incident high voltage beam, which is fired across through a specimen, which is thin-foil. And when it crosses a specimen, it interacts with atoms in the specimen. And this interaction process, you have elastic and inelastic process, which you see in the bottom, elastically scattered and inelastically scattered. The elastically scattered can provide a good signal to see images because they are scattered at large angle, and then they give contrast. Plus the material is thick and heavy. The inelastically scattered, it's more general, and then you can have to look at all the events, and this is why ILS, electron energy loss spectroscopy, can be so important, as you will see in the following of my talk. But these are the primary events. The primary events, but then once they have given energy to the specimen is in excited state, and it disexcites with different emissions and visible light and X-ray light. So, and these are the signals which can give you more information, and which when you will see to the multi-information and multi-signal microscopy. So what do we want to learn at the atomic scale? We want to learn the structure, the position of atoms. Then in a STEM, the important contribution comes from annular dark field, high angle annular dark field, HDF. You want to know the nature of atoms. Then you have Hills and the ADX signal, which can bring this information to identify the atom. And then the atom, you want to know how they are in detail organized and interacting with their neighbors and the neighbors, so you can have information about the bonding and the charge transfer between the neighboring ions there in the soil. And this is also carry also a lot of information there. And we can also look more generally at physical properties at the very low dimension scale. And then you have the cathodoluminescence. It is the emission of photons nearly in the visible, and there the nano laboratory, because it's only a small information that you get when you look at something at rest. But if you want to interact to induce some movement with temperature or the optical flux. No, here's what we want. So to do what we have mentioned that in many cases, the electron energy spectroscopy is important. So this is the plan of my talk now. I will discuss with discussion of the instruments that we have used in Orsay for years, and then discuss in more detail the delivered information by Hills and the fields of use. This is the second part. Then we will move from what I have already indicated in this introduction. We will move from single to multi-signal information, and at the end, if we have not too much time, a few words towards the future. So the first generation of Hills in the TEM there in Orsay began more than 50 years ago when I came and I acquired an Hitachi conventional microscope column. And for some reasons, due to the failure of my first research study for my PhD, my boss wanted me to see the vortices, and I could not. So at one moment, he said, Castin said to me, Colliex, introduce an energy filter in the column. And so this is the energy filter in the mid of the column, and this is a design on the left of the energy filter, which was a Castin and Henry filter. Okay. So by the way, we had also at that moment, because we wanted to look at specimen at liquid helium temperature, when I had designed and put in the column at the position liquid helium specimen stage. And I resulted at the time to record my first electron energy loss spectra at low temperature, at about 30 Kelvin, about argon gas which had been deposited on a thin supporting film. And then you see a spectrum, my first spectrum, the spectrum, and at that time, they had been recorded on photographic plate and digitalized by microdensitometer. And the energy loss axis was from right to left. It has changed after. And then you see the elastic peak and all the structure which we could excite there. The plasmon peak was about 16 eV, and the energy gap was 14 eV. So it's historical. The second generation of machines was famous VG, which I have shown you in the introduction. So this microscope, yes, I was very fond of it because I had discovered, listening to Crew there at the Cornell Congress, to Albert Crew, and spending a few months in the lab at Cavendish with Archie Owie, Alan Craven, and Nick Brown. I had discovered this, and I wanted one of them, and I could, after some effort, to get this one, which has arrived in 1980. So you see it in a room in Orsay, the column, the VG column, and at the top is a magnetic spectrometer. And you have the characteristics of this instrument down there. And Marcel Tancet in the mid, who was an engineer, thanks to him, we got the machine completely in development and very active over nearly 40 years. No, on the right, this is the basic design of a STEM machine. So with this one example, you had introduced on this machine with the parallel detection system, we had introduced the mechanism of STEM Hills acquisition and processing. So it is an example. There you have you see that this is an image of spectrum line across carbon nanotube filled with gaseous nitrogen. So the probe was scanned from A to B, and for this we had acquired all the spectra. So we had everywhere the graphite peak at 280 volt, and in the center you see there at about 400 eV. You see there at 400 eV, you see the small peak, which is the peak of nitrogen there. And you see that, for instance, this is the fine structure of the graphite carbon KH. So, next machine, which came in 2011. This is 30 years after the first one, survived for many years with the VG by itself. So this is a neon ultra-stem microscope. And then the gap between the first one and this machine was the introduction of aberration correctors. So we have an aberration corrector in this machine. So the probe size now was really in the range of 1 angstrom to 2 angstrom, and the other application, so energy resolution was 0.3 eV, something like that, and new generation of detector, and the spectrum imaging acquisition and processing system was now a routine development, and we recorded many energy filtered image with at atomic resolution with all the atomic columns. Okay, so this is the performance of this machine. In also, I have shown these two. For instance, the annular dark field, where you can see the two white points are corresponding to two atomic columns are separated by 1.4 eV. There, this is a scan. And in the energy loss, this is the detailed profile of two energy loss lines of M4 and M5 lines in Syria. And you see there also achieved 0.27 EV resolution. So we had progress. And the next and final generation of hills up to now, which have been delivered and is in perfect use in our lab in RC, is a chromatem from neon machine. And the development there from the ultrastem to the chromatem is the introduction of this box there. This box contains a monocometer, and it has been designed by Krivanek and Al at Neon. And now we have made a big progress in energy resolution. Because energy resolution, if you look, if you look at the zero loss peak there, you can have width at a maximum of 5 millivolts, which is what. And it is very important because if you look at the whole scale from whole dynamical scale from the center to the tail to look at what can see be, you see that at 1,000th of the maximum there, you have only 1.8 80 millivolts. So you can look very comfortably at structures, fine structures on the Hill's tail in this range of energy. And you have also a very good spatial resolution, as it is seen with a 70 picometer spatial resolution. So, to summarize, the performance of these microscopes has changed quite a lot over years. From two, I have selected two parameters: the energy resolution and the spatial resolution. The spatial resolution, what has been the big progress is the aberration correctors. The energy resolution, what has been the big problem, has been spectrometers, monocometer, and so now we can investigate new fields of plasmonics and now photonics, and have all this information, as you will see later. So on the right, you have a few important dates in this progress along the years, from the first energy filtered image in the 60s at Orsay and in Cambridge, and with at the end there with the top performance in Seattle. Okay. So I want also to mention, before going to the development, what is the multi-dimensional information, or a 3D space data cube, or hyperspectral imaging. This is what I call one bit of information, that is a number of electrons within an energy width delta E at a position delta X around X and Y. If I record all the spectra at all the energy position in the spectrum at this position, I have a 1D spectrum line. And there you have 2D with one filtered energy over the total XY scale. And these are the 3D, which you can obtain either by superposing energy filtered image and varying the energy loss which you record, or by adding close together all the spectra for all the position XY on the specimen. Okay, so this was the instrument. Now, what use are these instruments? The ILS and the field of view. So I have mentioned that we will do it in detail. There are three major spectral domains above 50 eV, which I call core energy loss domain. From 1 to 30 eV, moderate energy loss domain, and ultra low energy loss domain. Okay. Well, these are shown on this slide, which is a demonstration of all the information contained in an energy loss for an MgO, magnesium oxide specimen. So, and what is important is that this spectrum covers an energy domain, going from 0 to thousands of eV. So this is a very broad spectrum domain. This is about the only spectroscopy which covers a domain which covers in the light from infrared, deep infrared, to high X-ray domain. Okay, and you can record them at once. Okay, for one position. So you see that the domains of energy. This is the high energy or core energy loss. So going there, we have decreasing background coming from all the non-specific interaction during the solid, but you have characteristic energy losses. For instance, this is an oxygen K at about a little less than 600 eV, a magnesium edge, which, and the importance of this signal is that they identified the elements which are present on the illuminated area. The relative intensity also is important because it gives you an information of the abundance of this. And then you see that they are fine structures, they are not simple, and all the information about connection with neighboring atoms is contained in the analysis of these fine structures. In the plasma loss domain, you have also some intermediate and medium energy loss. You have information about all the electrons of the solid and the answers they give to the interacting primary electron either individually or collectively. But individually, for instance, then you have an energy gap, which comes energy, no sign of interaction below 6 eV. So this is an energy gap, and then the edge of the bond gap there. And very recently now is the advent of the phonon spectroscopy. This is typically where you are now with Monocometer. You can look at energy loss and peaks down to 70 and 77 millivolts, and you can discriminate them. So here we are. So first one, hyperspectral mapping of energy loss. So there you have a specimen, then you shine the probe on the specimen, and for each specimen, you record data. And as I already said, the information from the position, the intensity, and the shape of these edges. As an example, in the biological section, this foil, there is calcium phosphide, platelet, the particles. You look, this is a conventional image, you look at them, and then you can make annular dark field image. So you see that you have parts of the specimen which are heavy in the center, or on the around, okay? Around. So you have to go to hills, and these are typically hill spectra on the carbon and containing also, I think, when you are in the particle, you have a signal of calcium or phosphorus. No, no. And we can make an analysis using these signals, calcium and phosphorus, and you see that the phosphorus and calcium may be in the center of the organic material at the interface or around. And when you have a strong signal of nitrogen, it means that you have biological material. Okay. So now, with as already mentioned, we can go, and then this is what I call the nano hills period. And it was the golden age because with a group of Sumio Ujima in Japan, they developed and they built many specimens typical of nano tubular structures. And this is, for example, one of these nano wire. You see it, and when you go across this nano wire made of carbon, boron nitride, and carbon, and all in the vacuum, these are the elemental profiles of the boron, of the nitrogen, and of the carbon. And then this is a model of it, and you see there spectra characteristic of boron KH and spectra KH. And finally, after having performed a quantitative analysis of the importance of this signal, you can make a model. This signal was made of, this specimen was made of 5 layers of carbon, 6 layers of boron nitride, and 3 layers of carbon, as published by Sunaga in Science. And this has been pushed, this analysis, quantitative analysis, has finally been pushed to the identification of one single atom, always on specimen, absolutely wonderful specimens produced by the Japanese group and analyzed there. So this is what we call a people. This is a single wall carbon nanotube with fullerene carbon 82 inside, and they were stored inside the thing. And in each fullerene, there was a gadolinium, a single atom. This was a model, and this was the results. And then in the first results, we could detect a small particle of 3, of 4, and 1 atom. These particles were not automatically made of 1 atom because with the irradiation process at 60 kilovolt, you have some transformation and some relation so that some fullerene were destroyed and atoms were migrating towards their neighbor. And this has been confirmed a couple of years later by Ijima in Japan. And then this is an image where we have 2 single atoms, and this single atom, we have their spectra there, and they were made of typically lanthanum trivalent and cerium trivalent. So you have here the demonstration of the valence difference. Now, from single atom, now let's move to what we can learn with lattices. This is a typical lattice on which there were many studies. This is 2 specimens of titanium oxide doped with strontium and titanium oxide doped with lead. So typically we have the spatial resolution of the atomic column, obviously. And the contrast is that these columns in the bottom part are much whiter than the upper column. So the fact that this is much whiter, it is because they are made of lead. In the top level are made of strontium. But what was interesting was the evolution of the titanium across the interface. So this is an image, and this was a digital image, and we can see that if you add the lattice image, and if you have the pixel, the basic pixel was 0.05 nanometer wide. So if you had several pixels, you go to more extended pixels, but much more signal. And this much more signal, we can discover that when you go across the interface, there is a slight shift on this specific EEG L3 splitting. Okay, there. Where does it come from? So it comes from, after analysis in more detail and calculation, density functional theory, you have the strontium titanate and the lead titanate. And you see that there is this change of splitting between them. And when you look at the calculation for the two structure, the strontium titanate is cubic, and this one is tetragonal, distorted in the center. The detailed calculation of this, for instance, we see that for the cubic STO and the hexagonal PTO, there is a shift in these two parameters, in these two the distance between these two peaks. So in this case, you find the extended analysis of the fine structures has shown that it was locally due to a distortion, a crystalline distortion across the interface. Another example there on the other side, a rather similar specimen that we will see exactly the same. We will see a change of fine structures. Just to summarize it, these are cobaltates, tubular cobaltates, made of, I have the formula there, bismuth, strontium, cobalt, and oxygen. The heavy material is the bismuth. So in an dark field, you see very well what are the column of bismuth. These are the writers there. You see very well. Sorry. Between the column of bismuth, you have the other element, which constitute bridges there, and then you have column cobalt maps, strontium maps, and then the wall with oxygen, cobalt, and strontium maps. So, what is important? The important point which we have looked in detail is to look in detail at the fine structure of the cobalt. The cobalt, and then we go along the cobalt plane there. You select 4 cobalt lines. These intermediate are due to the strontium. And then you can make a distinct by a complex unmixing technique afterwards. You can show that this can have different states because for two columns of them, you had this peak. For 2 columns of them, you have the other peak, and they are due to 2 cobalt charge systems. So this is cobalt 3 and cobalt 2. So this is another example where a very detailed analysis of the spectra at high resolution shows you that you can be sensitive to the change of electric charge of neighboring columns. Okay. So I think that this has given to you a good feeling of what you can expect from coreless spectroscopy and detailed analysis. Now we are in the world of quantitative analysis to the level of the atomic level. Now, let's have a few words on plasmons. Plasmons have been historically the top specimen to be studied. And this is one of my first spectra in '68, which have been published there. And then the plasmon peak, you see this is this peak at 15 eV, we are at 16 eV, we are at silicon. When the thickness of the silicon foil increases, you have more and more plasmons excited during the crossing of the silicon foil by the incident electron. But I was very much surprised and happy to see recently in the journal Science a paper where they use the position of plasmon in detail to measure the temperature of the specimen. So that at first sight I would not have. And how they were using, the signal which they were using is exactly the position of the plasmon peak in the material. So this aluminium circuit on a support, the elastic peak, and this is the plasmon peak of aluminum. There is nothing really special on the experimental setup. This is a typical microscope with a field emission gun, but no aberration corrector, no monocometer. But what was the key of the success was the high signal. So with the high signal, you could measure, you could map, make a model now of the curve with a great accuracy. And with this great accuracy, you could approximate that the plasmon peak shift was about 0.54 millivolt per Kelvin. Okay, because what was important in this study, this was the fact that the position of the plasmon is related to the density of free electron. And when you increase the temperature, you take down the density because everything is expanded. And so if they could make this analysis and have this very beautiful, they could make a map of this circuit where you were introducing current. So there it was low temperature, and then in the medium, there was high temperature. Okay, that was just a case. Much more interesting in the following years, that is about the last 15 years, was the analysis of the response in small objects and close to interfaces. There was a local response, and this is our model, which have been systematically used. Historically, in the extended medium, this is there is something missing. There is that has been studied for parallel close to surface plasmons, for spheres where you have plasmons around the spheres, and for any type of specimen shape and dimension. So this has been was a nice paper published by our group, Jason Nalaya as the first author. It was looking at triangular platelet of silver deposited on a amorphous layer. And if you look at the specimen at the spectra recorded at 3 points, A, C, and B, across one of these platelets, you record this spectra, A, B, C, and outside the platelet, D, there was nothing in this energy range. And then you superpose the infrared, the visible, and the UV, and you see that you are really in the mid of the visible domain. And what was important is that when you made analysis, so you have recorded spectra along a line, you have clearly seen that there were from A to B, there were peaks at 1.75. We map them at 270, we map them, and at 320 in the center. So they were really localized at extreme positions on the specimen. This has opened completely the field of nanophotonics, as I would say, because there has been many studies at home in Orsay, but all around the world. And for instance, I show you this case where we have 4 specimens. These are the same scale. So this is a long nanowire, our small triangle in Orsay, a big triangle, an enormous triangle in Germany, or a nanowire much larger. Yeah. And when you look at the response under the beam, this is always localization of the response at extreme position, either at the edge or at the position at the tip, in the middle, or position along a wire. With the things, well, of course, I want to show you the extreme, more recent study of this type on a triangle. Now, this is always a triangle of aluminium now, of larger dimensions, and you see that you have the peak there at the tip, which is this one, E1, at the edge there, which is this one. This one, and you have maps, detailed map, but you see that you can, with the energy resolution, you have many more structures there, and you can make maps of this structure. So you have the edge modes there, and you I have problems because I want to show you on the screen the details which are interesting in my slides. Yeah, I'm sorry for that. Okay, so just some output of these studies about, you see that these are longitudinal and transversal oscillations of the electrons along the nanowires. So, and you see that there are modes. This is the first one. The second one, we have even and uneven and odd symmetries there, and different modes. These have been very well understood, and they are modelized, and you have the good modelization of the electric charge there, and the associated electromagnetic field and energy loss function. And in this experimental, in this comparison, you have been, for instance, in this case, this is one of these nano antenna of metal, of silver, I suspect. This is a mode that we see, you can find. And when you want to analyze exactly what happens there, this is the Hills, this is the experimental, this is the modelized Hills. And then what is important is that it can be explained by a distribution of charge and electromagnetic flux lines around the specimen. So now, with this example, we show that it gives you information on electromagnetic on fields, from smart fields, electric fields with it in this energy loss domain. So this is a continuation with a split ring resonator. We have the experiment, and you have the calculation of the electric field and of the magnetic field in this system. So now we come to the third part of this description of interest with when we go to the deep infrared. So in this case, here is again what I have shown, and so there clearly you can have very low energy plasma modes on a long copper rod. Okay, you can have, and besides that, when you are going below 100 millivolt, you are very sensitive to the vibrations of the atoms and ions in the specimen. These are a few examples acquired with a microscope equipped by Andrei Krivonek of a Monocometer. You have phonons in the top on left, it's phonons of hexagonal boron nitride, amorphous-silicon oxide. So this has been a quite new field of research and very rich field of research, which has opened about 10 last years. What has been shown is that they can extract phonons with two systems, a localized and a delocalized system. For instance, with beam very local, but looking at the energy loss at large angles, or a beam very far from the space, in the vacuum, and very localized. So this has been shown. So in this second mode, there when you, the first mode, I don't say, in the mode where you can average without too much energy, too much incident energy, you can have it in very sensitive system, guanine system. So going further, we recognize again the spectra which I have shown in the introduction. These are the phonon modes. These are longitudinal optical phonon modes in the MGO. MGO is a very favorite specimen for us, as you can recognize. And then you see that the peak at 70 EV is localized at the corners here. And on the faces. We have reproduced this type of experiment recently in the lab in Orsay, where we have made systematic series of experiments by tilting the same MGO nanocube at different angles and reconstructing the 3 modes at the corner, edge, and face. And you see that these are 3 millivolt energy difference. So we have begun a very sensitive domain and the map of this. So, well, signal to multi-signal multi-signal. So this is a microscope now equipped with technique. You can have the same monocometer probe, and then you can have 2 exit signals, one with electron energy loss and one with cathodoluminescence. Cathodoluminescence detector, and you can record it simultaneously now. And then an image of the topography, an image of the plasma map, an image of the photo image. So the strategy has been to introduce on the column this light output system. So there, the idea is below the sample, the electrodes are going this way. Below the sample, you have a mirror, you send the light as on a detector or a variable laser to introduce light. And this has been open because with this system there, because of you can modulate also the light analysis range, you can make spectra with a spectrometer, or you can make polarization, with also very interesting correlation of time of arrival between the different photons. And then you have, it has been shown that we are sensitive to single photon emission and opening broad areas of quantum electrodynamics. Here is an example there where you are on a flake of nanoparticles of hexagonal boron nitride. You can record the spectrum of the light emitted by this nanoparticle, or you can measure the time delay between the arrival of the different photons, and it gives information of the lifetime of the excitation, and you can check that, for instance, in this case, you are going towards one photon system, single photon. Okay, so this is summarized what we can do now with cathodoluminescence in different cases, and just a couple of examples on an archetypal type to show that we are now with, this is hexagonal boron nitride. We can record simultaneously the full electron energy loss function, major plasmon at 30 eV, a gap there at about 10 eV, and the phonon at about 140 eV. This is by monochromated hills. And by stem cathodoluminescence, you have the spectrum there of the line attributed to the Frenkel defect there, which is with all the satellites of the excitation of phonons together. This is the map, and this is the lifetime. Another example there, and now I try to cover as well as possible the superposition of information due to the acquisition of hills and cathodoluminescence. This is now on tungsten sulfur monolayer. This is one 2-dimension system. If you look at hills, you have the excitation of excitons there, in this XA, XB. In cathodoluminescence, the XB is forbidden there, you don't see it, but XA, you have on this so much better energy resolution, and you can detect what is called trion by the specialist of this domain. Okay, and this exactly, I show you this slide because this is exactly the present field of research that we are entering and going into details there of this system. With there, you have the superposition of the atolite system. This is the introduction of the system which is used for cathodoluminescence and so on. And this is the specimen holder for liquid temperature, liquid nitrogen temperature. So now we are close to the end of the talk. what are we doing now in Orsay? There are many studies, many developments on basically on detection and processing of spectra, because as you have understood, we have moved from an era where one spectrum was okay. Now we have millions of spectra every day. So this is a need for computer assistance and development of computer assistance. So these are a few lines of work now, assistance. I want to illustrate a couple of words. For instance, electron energy gain. So I was very sensitive to electron energy gain because I have spent all my life in studying electron energy loss. So I want to gain energy, and this I was very enthusiastic with the work of Zigwell when I saw this type of spectra that he was showing, for instance, when firing an electron on a carbon nanotube. But the trick was that carbon nanotube had been illuminated by an electron which had created an evanescent optical field, and then the next electron could measure the field which had been created by the first one. And this is why there were these superb spectra. In Orsay, we had not the possibility to create new guns with filtered energy by illumination of laser. Pardon. But we have developed the technique of blanking plates on the detection. So the detection gives you the time scale to measure. These are, for instance, on a specimen of nanoparticle of silver there, I suspect. This is without the illumination by this laser. And there you have two peaks depending on two positions of the spectra. These are two energy loss. But when you illuminate with the laser, it is excited, and when you look at the spectra at these two positions, now we have the zero loss, but we have the same structure on the energy loss and the energy gain. So energy gain, so we could now have access to all the domain of excited states and nanoparticles. In more detail, this is what happens when you vary the wavelength of the illumination laser by a small wavelength, 15 nanometer. Then you have a change, and you see that the excitation varies at the top of this particle. So last slide, nearly two last slide. Another application of phonon. Phonon now, where you look at the center of nanoparticles. This is, I think, again, MGO. Okay, this is what happens. So you measure in large angle there, you measure the energy gain. And this is the spectrum of there at different temperatures. So this is another way of measuring temperature, which has appeared recently in the literature. So you have the energy gain, the energy loss. And due to a principle which means that the ratio of this intensity of loss divided by gain, or the contrary, it depends on the temperature linearly. And this has been checked on this example, and these are temperature curves detected from the energy gain. So thermometry. An example now of what you can do with temperature variation. This is the detector, the specimen stage. And then what you can look there, nano domains in V2O3, when you run the temperature, you cool it from 100 by 1K, and you see that when you cool by 1K there, you have a change, the disappearance of a plasmon peak there. And when you heat it again on the left, on the right, you see that you have also the appearance of this. And when you look in detail there, I cannot see it, you see that there is a front. When you heat it, there is a front where you move, the transition is realized. Okay, and I will just mention the title of this final slide. This is event-based hyperspectral hits. This is a new approach to the creation of maps, different maps. This is what we were doing traditionally in A. This is a frame acquisition, a frame-based acquisition. Each spectrum is acquired, entire spectrum is acquired at one time for one position. And now we support it by event-based mapping, where you are using, this is on the right, you are using two scan units, one which is a basic scan normal, and one which is sensitive to the appearance of events, and we have a very fine time discrimination. The normal one is typically with a time resolution of tens of milliseconds. Now this cheetah time peaks mode is an approach domain of nanoseconds. So this is a real opening, and we expect from it a lot of developments. So I have finished my talk. It has been difficult at some time because I was not mastering very well my screen. So what I am doing now, year 2022, I have written papers, review papers. It has been published in this journal, and this is, for instance, this paper. And this is a group which have worked. This is not the most recent one, but you have the group with people, important people. I am there, but I was returned at that time, and the chief was Odile, Stefan, but you have Mathieu at the prime, Marcel also. Thanks to my colleague in the group, and to all those who have worked with me over the past, because that's covered now. I have been hired by CNRS in 65 and 22. It means that I have been hired by CNRS for 57 years. So tomorrow, I will go back to my house in Normandy, and through my office window, I will look at the opposite meadow in front of it. Thank you very much for your attention. And sorry for the wiggles which I've induced during my presentation.